The previous page covered distinct real roots, but another thing can happen is you actually get a repeated real root when you solve the characteristic polynomial. Alright, so to outline that, we do our regular guess, where we guess y is equal to e to the rx. We get our characteristic polynomial, so we end up with a r squared plus b r plus c e to the rx equals 0, 0. I'm going to go ahead and take an a out of that, so not worry about it. And then you end up with r minus r1 and r minus r2, the two roots. We get e to the rx equals 0. Well, what if r1 equals r2? So then we have a little problem. So right, we always say, okay, well, we have two solutions. y1 equals e to the r1x. We have y2 equals e to the r2x. But if r1 and r2 are the same, then y1, they're equal pretty much. So how can we have two different solutions if they're the exact same solution? Because r1 equals r2. What if both the roots are the same? Well, so there is a way to solve for this that isn't just a guess. It's called reduction of order. Close enough. You will learn about it later on, but for now, you can solve this. But for now, use y2 is equal to x e to the r1x. And that'll be your second solution in the case when you have a repeated root. The reason that works out is you kind of get half the product rule disappears when you do this bit. So let's go ahead and take an example. Let's say we have, what's a good one? Let's do y double prime minus 2y plus y equals 0. Well, if we solve that one, we're going to end up with r squared minus 2r plus 1 e to the rx for our guess equals 0. And this factors into r minus 1, r minus 1. So then, right, if they were distinct real roots, we would have y1 is going to be e to the x. We'd have y2. We can't write e to the x again, so we're going to write x e to the x. So this one, you probably believe me that if you plug it into the differential equation, it'll work. Why will this one work? So let's go ahead and do that. So we'll go over here. This will be enough room. So let's try it out. So we've got y1 double prime minus 2y1 prime plus y equals 0. Right, if we plug that in, we take two derivatives of e to the x. It's still e to the x. So we get e to the x minus 2 e to the x plus e to the x. And yeah, that does equal 0. And if we factor out the e to the x, we end up with 1 minus 2 plus 1. E to the x equals 0. Okay, well, that was the y1 solution. What would the y2 solution look like? Well, same thing. So we plug in y2 double prime minus 2y2 plus y2. That's supposed to equal 0. And now we got to compute some derivatives. So over here, let's compute y2 prime. Well, that's going to be a product rule. And I'll need a little more room for this. So yeah. We have y2 equals x e to the x. We have y2 prime. Okay, well, that's a product rule. So let's do the derivative e to the x first. So this half is x e to the x. Then I get plus. The x turns into a 1, so I get 1 times e to the x. Right, and that's the same thing. I've tried to simplify this as much as you can, so you don't have to take as many product rules and derivatives. This is the same as x plus 1 times e to the x. Right, if you want y2 double prime, okay, well now I take the derivative of this. I'm going to leave the x plus 1 alone, so I get x plus 1 times derivative of e to the x, which is e to the x And I get plus the derivative of x plus 1 is 1 plus 0 times e to the x. And if I simplify that, that's going to be x plus 2 times e to the x. Okay, well now I've computed those, I'm going to go ahead and plug them in over here. So y2 is x plus 2 e to the x, and then minus 2 times y2, prime right there, is x plus 1 e to the x, and then I get a plus a y2 x e to the x. And that is all supposed to equal 0. So what I'm going to do is I'm going to separate out like terms. So I'm going to have a parenthesis, there's going to be a few terms here, I think just 2. Those are going to be the x e to the x terms. Then I'm going to have plus, I'm going to have some, I don't know, I think 2 maybe, e to the x equals 0. So here I have e to the x times x, so I have 1, and then I have minus 2x e to the x, so minus 2, and then I have a plus x e to the x, so plus 1. And then for just the e to the x terms, I have 2 times e to the x, then I have a minus 2 times e to the x from here, and then there are no e to the x terms all by themselves over here, so it's just plus 0. And yeah, that does work out. Kind of intuitively, the reason that it works out is all the times you took the derivative where the half of the product rule you just did e to the x, you ended up with the same looking thing as when you just did e to the x by itself, right, leaving the x alone. Right, I got the 1 minus 2 and plus 1. 1 minus 2 plus 1, x e to the x, for the half of the product rule where we only took the derivative of e to the x. But then the other half of the product rule that ended up being the x's, that one also canceled out. And that's the interesting part there, that it worked. But that's what you do, and this is why it works. And if you actually plug it in, it does work out. You have to do product rule now, which is a little annoying, but it does work out.